So the next topic in this series about managed blockers will show how to encapsulate the managed blocker interface in a more civilized way, or a more civilized interface or civilized API. And this will demonstrate something called the blocking task. And we'll show how you can use that to apply to blocking I/O operations, yet another use case of this approach. So there's a there's a class called BlockingTask. And this BlockingTask integrates blocking suppliers using the thread pool. In this case, we typically use it with a common ForkJoinPool, but you could use it with other thread pools as well. So here's the BlockingTask class. You can find this in my EX20 folder, EX20 project in the Java 8 folder in the Live Lessons GitHub repository. So BlockingTask is a class that I wrote, and you use it, or you've used it in assignment 1. You'll use it in other assignments as well. And what it does is it encapsulates all the low-level gobbledygook of using ManageBlocker, so it's way easier to program rather than having to recreate that yourself. So here's the main method call in ManageBlock. You can see it's a static, generic method, and it enables blocking suppliers to use Java ForkJoinPools. We use it for the common pool. It could be used for other pools as well. The way it works is it creates a helper object, which we're going to look at in a second, called supplier ManageBlocker. And we give that the supplier parameter. So we pass it a supplier. That's going to get encapsulated in this object. And once we've made this object, which we'll look at its implementation momentarily, we then say ForkJoinPool manageBlock, and that submits that to the ForkJoinPool, whatever one happens to be calling. We're using the common ForkJoinPool here, but you could use it for other ones as well. And this is going to block until the operation that we passed it is done. And when it's done, we're then going to go ahead and say, hey, ManageBlocker, now that you're finished, please give me back the results. So you see there's a method defined on supplier ManageBlocker that returns the result of the blocking call. So this is basically how the implementation works. Now, you don't really have to know how this implementation works at all. You just have to know how to call in ManageBlock, passing in a supplier, which is great, because that's the whole purpose of abstraction, is to define a new level of semantics, new semantic level where you can be very precise about the meaning without worrying about the implementation details. So let's take a look now at the supplier ManageBlocker class, which implements the ManageBlocker interface, which is a nested interface in the ForkJoinPool. And you'll see here we have a supplier, which is tucked away, and the constructor just stores the supplier parameter into the mSupplier field. We have a couple other fields here. We have something that keeps track of whether we're done or not. We also have something that keeps track of the result. So let's take a look at the most important method, which is the block method. This is the one that's going to get called so the supplier that we provide can block while allowing the threads to be compensated in whatever pool we're using this with, so they will grow by 1, even if the supplier happens to block. So you can see what we do here is we say mSupplier.get. Get is a method you can call on a supplier that will do whatever the supplier is doing. And we get the result back. We set mDone to true, and we return true. This indicates that the result has been obtained. The isReleasable method just returns mDone, which starts out being false, because there is no easy way to know whether this can be used in a non-blocking way. So there's no non-blocking behavior for a blocking task. You're assuming that the call is going to block, although we could have made it a bit more sophisticated if we wanted to, but we didn't do that. GetResult returns the result. When GetResult is called, the blocking will have finished. So there's a whole slew of examples of doing this. This example, this EX20 program will show you how to do this. Your assignments 1 and 2 also do something almost identical to this. It's called something a little different. I think the method's called something like, I don't know, ManageBlocker download image or something like that. But this example has one called blocking download, where you give it a URL, and it takes the URL and turns it into an image. And how does it do that? It calls the BlockingTask call-in manageBlock method, passing in a supplier. Supplier is just a supplier lambda that will call download image with the URL. Now, download image is indeed a blocking call. If you search around and take a look at the implementation of download image in Android Studio, you'll see that it basically sets up a connection to the URL, and then it blocks reading the contents at that URL from the remote server, puts it into a buffer, and returns it as an image. And the cool thing about this is this will expand the calling thread pool to handle the blocking image download, without you having to write all this additional code to deal with managed blockers and so on. That is done for you by the BlockingTask wrapper. So really helpful class that makes your life a lot easier. And what will happen here, if there's extra threads that are created because you've got a bunch of these downloads happening concurrently, then once the burstiness of that particular set of downloads has finished, then the ForkJoinPool will reap them and will go ahead and they can be reused sometime later, but it'll return that memory back to the operating system in the Java runtime environment. The current limit of the number of threads that can be added to this pool is 256. And this is defined in this property, Java util concurrent ForkJoinPool common maximum spares. So at some point along the way, they might change that, but that's what the current value is if you poke around and find this. The only real downside with this approach is that if you add a lot of threads, now notice we don't add an unbounded number of threads. We only add up to 256, which isn't too bad these days. But you can start to saturate the CPU cores during bursty workloads. So if you have a lot of work coming at one time, a lot of threads will be created. And even though that's often a good thing, you can end up chewing up a lot of resources by doing that. Keep in mind that the threads that are being created here are platform threads, not virtual threads. So as a consequence, they take up real space. Now, having said that, 256 platform threads is not too bad. Most modern operating systems and most modern hardware will handle that very nicely without even breaking a sweat. But just be aware that you can cause more CPU overhead by having lots of those threads running around. OK, so that is the end of how we encapsulate the Java Fork Join Framework's ManageBlocker interface.